everybody can hear me. Today morning, the first lecture will be on electromagnetic physics in Geant4. It's even a bit more special than this because, as you can remember, Vladimir was probably talking about the different physics, electromagnetic physics that Geant4 covers. And today I will focus on some special topics regarding more that we call standard physics, which is used in the intermediate high energies and mainly for detector simulation. And as you will see, there are some special things that we need to do in this case, in this energy regions, in order to get to a point actually where the simulation is feasible. You will see that we need to apply some approximations. Otherwise, we would not be able to do simulations. We would be able to do, but it would be not feasible. It would take 100 years to get a simulation result. Well, since we need to use approximations, I would like to mention a couple of these approximations that we are using and what are the consequences. So for you as a user, what is the message of this collection of topics that I would like to discuss a bit today is that I hope that you will see the effect of this approximation and how you can deal with this approximation in your situation, in your given simulation, in such a way that you make sure that you keep the limit of the approximation, because your simulation can go just very, very wrong, the result, if you violate this approximation. So what are these special topics? Many things will be related with energy loss processes. We will get soon there what I mean here. We will talk about secondary production threshold. What is it, why, and how you can set proper values. Those who were with me in January for the 3 years beginner course, if you remember, we finished the third day with an application where we actually reached this point that we were able to do a simple simulation. Where I even showed that the secondary production threshold plays a critical role. It's a critical parameter in order to get proper result or not. But I did not say anything about what the secondary production threshold and why in that application it's critical. So today I will do all these things and you will understand and you will hopefully see how to set a proper value for your simulation. Then I would like to talk about a few things regarding regions. Regions is a geometric concept, but we rely on it heavily. Even when we set production threshold or any user actions, it's a very, very useful concept that is available in Geant4, and we make a lot of use of it. Then, of course, there will be some consequences of the approximations that we are doing here, that we need to use some energy loss fluctuation model. You will understand why. And also the continuous step limit, what is it, why, and how it comes from all these things. Then, as you can see, the second main point is models per regions. And again, here, as I mentioned, we make a good use of this concept of region, detector region. I will show you how to set a special model for a given part of your detector, why it is useful, how you can do it in a couple of different ways. And one important thing in the intermediate and high energy physics simulation is how you describe actually Coulomb scattering of especially electrons and positrons. Because this can change many, many things regarding the speed of your simulation and the accuracy of your results. So I would like to say a couple of words on that. So let's start with the first topic. The main topic is energy loss processes, and within that, secondary production threshold. So let's see what is the secondary production threshold and why it is introduced actually in the simulation. So we will focus on Bremsstrahlung photon emission. And if you see on the right, on the top, here, I hope you can see the note, you can see this plot. And this plot shows actually Bremsstrahlung photon emission differential cross-section. Differential in the emitted photon energy, that is key here. When an electron with 1 GeV moves in a silicon target. And you can see this is the differential atomic cross-section. But what is important here to recognize, and why I'm showing this, is that if this differential cross-section, what tells roughly, is at a given photon energy, you get the emission rate. And if you see that we go down with the photon energy, then this emission rate goes up. It means that many low energy photons are emitted by electrons in Bremsstrahlung. No, this is not very good. This is not good because actually you need to handle these secondary photons in the simulation. So you need to take them, you need to track them, which is not really feasible. So there are so many, you can see, at low energies, emitted with very low energies, that would not be really feasible to take all of them and simulate their transport. But we are in a lucky situation, because if we see how far these low energy photons go, we see that they actually doesn't go very far, because the lower the photon energy, they will be absorbed very fast. So this is a good combination, because these two things makes the next point, this A and B, actually the two situation identical, which means that if you are in a detector, where actually in a detector volume, where I'm saying no, volume is your actually spatial resolution of your readout. So there is a given size, and within that size, you cannot make difference between different points inside that volume. So if you are in this situation, then if we generate photons that would not go out from your volume, and we track them really one by one individually till they be absorbed, or we don't even stop the primary particle to generate, but we account that these photons would have been generated, their energy would have been taken away from the primary, but it's deposited immediately at the trajectory point, that eventually you don't see the difference, because the deposited energy stays within your spatial resolution. So I hope this makes sense, and this makes possible to speed up actually the simulation of Bremsstrahlung photon emission, or actually simulation of electron transport with Bremsstrahlung photon emission with at intermediate and high energies. Now, one thing that you might recognize here, that I'm talking about spatial resolution, which is we are talking in length, size of the volume, and on the same time, I'm talking about energy, like low energy photons doesn't go far. So this will come a couple of times, the energy and length energy question. We will get back to this. Don't be confused with this at the moment. So far, we saw that it's not a bad idea actually introduce this secondary photon production threshold. And how is it introduced? Actually, we introduce an energy threshold for secondary gamma production in case of Bremsstrahlung. That we say that if the secondary photon energy would be below this threshold, then we do not generate explicitly these secondary photons, which means that we do not even stop with the electron, primary electron, to generate it, but we account all the energy that would have been taken away by these subthreshold secondary photons from the primary as a continuous energy loss of the primary particle along its trajectory when it moves from the pre to the post step point. Okay, and this continuous energy loss, as you can see on the top equation, actually I show, but it's not so important. It's described by a mean quantity, the stopping power, which is in this case called restricted stopping power. And you can see this covers the complete differential cross-section part from 0 up to the secondary photon production threshold. And we compute a mean energy loss value per unit step length, and we count this subthreshold photon emissions, actually the energy loss caused by this unsimulated subthreshold photon emissions, by this mean energy loss value along the step. On the other hand, everything that would result in photon emission with secondary photon emission in Bremsstrahlung with an energy, initial photon energy, higher than this production threshold, we simulate really as individual interaction. We stop the electron and we will emit a secondary photon, and the secondary photon will be tracked later. Okay, this contributes to the discrete part of the description of the Bremsstrahlung photon emission, and actually you can see it described by the corresponding cross-section, actually again a restricted cross-section, because you can see that this integral that gives you the cross-section covers the upper part of the differential cross-section from the secondary production threshold up to the maximum possible energy. So with this, actually, Bremsstrahlung photon emission is divided into two parts. One is called continuous, the other is discrete in the Geant4 terminology. Actually, all middle and high energy particle transport simulation codes will need to use this technique in order to be feasible, the simulation of the interaction. It's, again, we do it not because it's not possible in another way. It's possible in another way, but usually we don't have 10 years to wait for a simulation result, roughly. We have been talking about Bremsstrahlung photon emission. I could repeat roughly the same things talking about ionization. When the electron, for example, participates in ionization and producing a secondary electron, the same concept and image would be seen there. The difference is the secondary particle in ionization is a secondary electron, so we have secondary electron production threshold there, and the absorption length there is actually range. Now, we get to this question again that, as you could see, when we are talking about the secondary production threshold, we are talking about an energy that actually gives a limit in the integral. But on the same time, when you want to imagine what would be the proper value of this energy, you actually need to translate this energy to a length, because we were talking about a spatial resolution. So you need to select an energy that corresponds to a length, in case of Bremsstrahlung photon emission, in such a way that secondary photon with that initial energy would be still absorbed within your volume that represents your detector volume, that represents your spatial resolution. Okay, so there is this, again, this energy length question. So this question regarding, we should give the production threshold in energy or length. We can say a couple of words, because actually different simulation toolkits will have a different decision on this line. Some will require the user to give the secondary production threshold for secondary gamma production in Bremsstrahlung and for secondary electron production in ionization in energy, which is not bad because this is actually how it is used at the level of the model. We saw it's an integral limit. It's very nice. However, it gives some difficulties because, as I mentioned, eventually when you would like to know what is the proper value in your case, you need to think about your size. I mean, not your size, but your detector size, your volume size, your resolution. So you need to think in length. And if you choose one energy, then it will translate to different length, different absorption length or range in different materials. So actually, in each material, you should choose a different production threshold in order to keep the same length. So if you have two volumes with exactly the same size, but one is a light material and the other one is a heavy material, then you should choose a drastically different secondary gamma production threshold in the two different volumes. Now, also, the proper value will also depend on the particle, whether you should, whether you have electron or gamma as a secondary particle. So all these things makes a bit complicated to choose a proper value in energy. So the other possibility is to choose a value in length, and then that value can be translated to energy. And when Geant4 was designed, it was thought that this is more intuitive and easier for the user to ask them to give the secondary production threshold in length. And this actually what's happening in Geant4. So you as a user, you need to set secondary production threshold if you want, because it has a default value of 1 millimeter. And in the reference physics list, actually it's 0.7 millimeter in length. And actually when the application starts and your detector is constructed, so we know what kind of materials you have, then the length given by the user is automatically translated inside Geant4 to the given energy value, which is an absorption length or range depending on the particle. So if you are not happy with the default value, and I can encourage you to make sure that you are perfectly happy with the production threshold value, which means that you need to make sure that is correct. You will see why soon. Then you can set that value either in your physics list. I'm not sure if Vladimir was talking about the physics list, but one of the interface methods that the physics list provides is actually set cut, where you can do this. Or you can use simply a UI command, run set cut, and you give the given value with the unit. Or you will see just soon that what particles has production threshold, but we already mentioned electron and gamma, and you can set a given production threshold value, special for electron or gamma or the different particle. Now, there is a minimum value. So if you set a very small length, it's actually not the length, but the length and the material is important when we translate, and also the particle, when we translate it to energy, then there is a minimum value. Whatever small energy would be the final result as a production threshold, a secondary production threshold, there is a default minimum value of 990 electron volt, This is because that most of the approximation, even this near 1 kilo electron volt production threshold that we are using actually, when we are using condensed history simulation that we are talking about at the moment, it's already a bit high. It can, however, set to be even lower, this minimum value. So you can see this cut set low edge command, UI command. You can lower this value even to 500 electron volt. I would not recommend to go down. I would even recommend to go a bit up if you want to be more correct, actually. But of course, if you have a good reason and you know why, you can lower this secondary, minimum secondary production threshold energy. Now, we saw already that electron and gamma particles has production threshold. You can set production threshold for electrons and gamma. The gamma production threshold is used for the secondary photon emission in case of Bremsstrahlung. The electron production threshold is used in case of secondary electron production in case of ionization. But beyond that, Geant4 provides the possibility also to set a secondary production threshold for positron that might be used in case of pair production, but it's not really okay. So I say this for completeness, but you can ignore unless you have a really special reason to go into this direction. And one special thing is proton secondary production threshold, but this is actually a rather different story here because it's used in case of, as a kinetic energy threshold for nuclear recoil in case of hadron elastic interactions, for all hadrons and ions. That's more or less one important thing that it can be also, I must say, crucial in many cases, is to keep in mind that when you set a secondary electron production threshold, by default, you don't suppress all the secondary electron production during your simulation that would have an energy below that threshold. Because that threshold is applied only in case of ionization. So in case of Compton scattering, for example, the secondary electron is always produced, no matter what is the energy of the secondary electron. However, there is a flag that you can turn on. You can see the UI command process EM apply cuts and true, which will apply the production threshold in all electromagnetic interaction. If you turn it on, then you should not see secondary electrons coming from electromagnetic interactions with an energy lower than the production threshold. Now, you need to see some difference between what we have been discussing so far, how the secondary production threshold is used in case of ionization, and in case of these interactions, like in case of Compton. Because the main difference is that the photon producing that Compton electron is stopped. The interaction is invoked. The secondary electron, in case of Compton, is produced. But if you turn on this flag, apply cut, then we just take the secondary electron and immediately deposit the energy. Okay. While in case of ionization, the primary particle, the primary electron, is not even stopped to produce that secondary electron. So, for example, it can be a really good test that you think that you set a proper secondary electron and gamma production threshold in your simulation. Then you turn on this apply cut that will apply the secondary production threshold for all EM interactions. And if you see any difference between the two simulation results beyond the speed up that you see, then it means that your secondary production threshold is probably not a good value. You will see a bit more why. Again, but I think I mentioned already this couple of times that this using secondary production threshold is not mandatory. We can do simulation that makes much more easier the whole life without condensed history simulation, but this is not feasible. So it would require creating a secondary particle, tracking that secondary particle. It requires lots of resources during the simulation and lots of time. So I would like to show an example how to set a production threshold and actually what is the effect of the secondary secondary particle production threshold, or in Geant4 as we call cut, secondary production cut. So you can see here on the right our very simple simulation setup. It's a very thin target, 5 micron silicon that we hit with 45 MeV electrons. And what we are recording during the simulation is a mean energy deposit. And this mean energy deposit is plotted on the left side on the plot, as a function of the secondary production threshold. Here the secondary production threshold is the same. We set a value here, for example, starting from 1 micron, both for electrons and electrons and gammas. You can see we increase this secondary production threshold, and for a while the simulated mean energy deposit doesn't change after it starts to increase. And why it's increasing? It's simply because you can see that it starts to increase when already around 5 micron secondary production threshold. After it will increase rapidly. So what's happening is that actually, as I mentioned, when you say that your secondary production threshold is, for example, in this case, 2 micron, that what you need to keep in mind that you actually say that you cannot make a difference between a photon that would go less than 2 micron and would deposit the energy within the 2 micron range. Okay. Wherever that energy would be deposited within 2 micron, for you it's the same. So in our case, as long as the energy of the secondary electron or gamma emitted by this primary electron in the silicon target would stay inside the silicon target, then from our simulation point of view, there is no difference. The difference starts to come when actually we don't generate secondary gamma or secondary electron particle inside the silicon, and we think that it would be deposited inside the silicon, but actually those would leave the silicon and they would take away that energy. So when your secondary production threshold starts to be too high, you are making wrong assumption, then you start to be on the wrong side of this curve. Okay. So I hope that this shows very well how important is to set a proper value based of secondary electron production threshold based on your spatial resolution of your detector volume. And why it is giving you a performance increase or actually computing time benefits, you can see on the last column actually, because you can see for 1 micron the secondary electron production threshold is below actually 1 kilo electron volt, 2 micron is nearly 3 kilo electron volt, and 5 micron is 13 kilo electron volt. And on the last column you can see the mean number of secondary electron produced. So when you move to 1 micron to 2, you immediately reduce by down to 30%. And there is a huge reduction immediately again when you move to 2 to 5, the number of secondary electrons. The gamma, no, because the gamma production threshold actually in energy that corresponds to 125 micron in silicon would be far below the 1 kilo electron volt. You can see it's this minimum threshold value for a while. It starts to increase here. But you can see that this is where the benefit comes from when you have a higher and higher production, secondary electron production threshold. You are producing significantly lower and lower secondary electrons, while your result is stable, doesn't change at all. So just a couple of words at the end of this production threshold business. Is that it's important to make a difference between secondary production threshold and cut and tracking cut. If you are talking about tracking cut, it would mean it means something that that whenever, if you introduce it in energy, for example, that whenever you are tracking a particle, when its energy drops below that threshold, you stop the particle and you don't track further the particle. Now, in Geant4, there is no tracking cut by design. We will see soon that there is a mechanism that makes sure that all the charged particles, for example, are ranged out, which means that eventually they will deposit their energy nicely at the end of their trajectory, and their final position point will be in the proper place. Because introducing a tracking cut in energy could lead to this problem that you are somewhere in your detector and you introduce a 10 kilo electron volt tracking cut and you stop the particle wherever you are and you deposit the 10 kilo electron volt, you deposit the remaining energy of your particle that is somewhere below 10 kilo electron volt. But you deposit where you are, okay, where the particle is. What will result in this ranging out the particle is actually that there will be a final step where we put somewhere this electron, this particle that more or less corresponds to this proper final position distribution. You will see how it works soon. So why I'm saying that there is no tracking cut in Geant4, there are something that we call user limits. And I think yesterday or tomorrow, I don't know exactly, this topic will come. You can introduce a tracking cut, actually. You can introduce a tracking cut in energy, track length, time, and so on and so on. So you, as a user, you have the possibility to apply tracking cut. Moreover, actually, there is a tracking cut introduced in Geant4, but not by design, okay? So this is very important difference. This tracking cut that has been recently introduced, you as a user with the UI command, you can set to 0 and everything will work fine. However, this usually low energy maximum for electrons, for example, electrons, positrons, is maximum 1 kilo electron volt, this tracking cut in the reference physics list constructors, EM constructors, and it has the reason why it has been introduced. It's purely a performance reason and runtime reasons. It was to kill some low energy charge, very low energy charge particles that in magnetic field they would loop practically forever. Okay, but as a user, you can all the time set it to 0 and everything will work fine, even without having any production, any tracking cut. Okay, so let's move a bit further, but still on the production threshold line. I mentioned that region is an important concept in the detector that we are using actually heavily during the simulation, especially when we have a complex detector. So that example that I showed with the silicon, it's a very simple example. Most of the time, you have more complicated situation than this, especially if you think about high energy physics detector simulation. These are very complex detectors. So complex detector means that there will be different part of the detector with a different granularity of information readout, and the different part of sensitivity, where sensitivity in this time means that there will be some part of the detector where you would like to see more details and more detailed simulation, and some part where there is 10-meter concrete, then you don't care too much what the heck is going on in 10-meter concrete. So you would like to be able to set different production threshold because you have different spatial resolution and different interest in granularity of the simulation, different part of the detectors. And this is exactly what the region concept gives you, among many others, that actually, if you remember in the geometry lecture, then you can define regions in your detector and you can assign volumes to a given region. And you can set production, secondary electron production threshold for a given region. So when you set a production threshold, by default, there is a region that's the default world region. Even if you don't define any region, there will be one region. This is the default world region. All your detector is inside this region. And when you set a production threshold, then you set actually for this region, which means that for your all detector. However, there is the possibility to introduce your own region. And I show here an example. If you go to examples, extended electromagnetic test EM3, which is actually a simplified sampling colorimeter simulation, then you can easily create your own region and assign some volume to that region and set a different production cut in that region compared to the other part of the detector. So in this test EM3 example, what you have is a simplified sampling colorimeter, which means that actually you have some layers, repetitive layers. Each layer is usually composed with the light and the heavy material. So one layer is, you can imagine, for example, like a box that has two parts. The first part is like lead or liquid argon, and the other part is lead or liquid argon. Okay, it's a kind of sandwich, and it's repeated many, many times. Okay. So what's going on here, I show how you can set a G4 region, your own region, sorry, that we call here the name own region, in your detector construction. Very simple, you just create the region, as I show here in the first line, giving a name. The name will be important because you can refer later the region. And you just create a production threshold value in length, which is 0.1 millimeter in this case. You create a cut object and you set this value, and you register this cut in that region that you are created. Okay. Then, if you have the region, you set up the production threshold, you can add a logical volume, which is this F logic absorber. What I'm adding here is actually the liquid argon part of this detector. It's as simply as this. And when you run the simulation and you see the printout after the beam on, you can see the report of what kind of material cut couples and secondary particle production threshold you have. And in the first case, you can see that the first material is galactic, is actually filling out the whole world. And you can see the region here of this, where this material is sitting, is the default region of the world. Then the second, the lead, the same default region of the world. And in green, I show our region that we just created. The liquid argon is indeed in our region, and you see that on the top the production threshold is 0.7 millimeter. As I mentioned, it's the default. You can see actually I set it here, And in the region that we just created, we set 0.1 millimeter. So indeed, everything works just fine. So here, this is how you can make use of regions to distinguish between the different parts of your detector, where you would like to see more detailed simulation, or where your spatial resolution is different than the other part of the detector. So, so far we have been discussing a secondary production threshold, and I mentioned that the subthreshold secondary gamma production in Bremsstrahlung, or the subthreshold secondary electron production in case of ionization, is described by the corresponding quantity, mean energy loss per unit length. That's called stopping power. And we compute actually the energy loss, the mean energy loss, due to this subthreshold interactions, while the particle moves from the pre to the post-step point. And what was the key word in this is the mean. So imagine this simple experiment that I showed just before, the silicon, this 5 micron silicon. If we describe the energy loss just with this, the subthreshold energy loss, just with the stopping power, we will get a mean value. So as long as each electron passing through the same path through the silicon, which means that the same step length, they span the same step length because they have a high energy compared to the thickness of the silicon, then what you would be your energy distribution, we simulated only the mean, if you remember, what would be the energy distribution based on purely on the stopping power would be a delta function. You would get the mean value. But this is not true, of course. So in case of condensed history simulation, when secondary production threshold is applied, we need to use an additional model that actually gives us the subthreshold energy distribution. If we know what is the mean energy distribution, we ask the fluctuation, the energy loss fluctuation model that tells us what is the proper distribution, actually. I show this just for completeness, and it's also good to keep in mind. Actually, there is a UI command that you can do simulation by turning off the energy loss fluctuation model. So in this case of silicon, if you do this simulation, or if you were there with me in January and you already have this simulation, then you can, with the UI command, you can turn on and off the fluctuation. And if you turn off fluctuation, you will get a delta peak here. If you turn back on your fluctuation, you will get this nice distribution, actually, that we also got when we tried our final version of this application in January. No.
Excuse me.
Sorry?
May I have a question? On previous slide?
Yes.
Yeah, on the x-axis you are showing the channel number in the above figure.
Yeah.
Channel number.
Yes.
What comes up in the Geant on the x-axis?
Sorry, I could not hear the
So it is a combination of simulation as well as experimental work. The first figure on the top. On the x-axis it is channel number. What comes up exactly in Geant?
It's up to you what comes. I mean, this is an application. I mean, this what is on the X is some kind of energy loss related quantity. Okay.
Okay.
It's because it was chosen that the experimental data is in this unit, if you want to talk about like this. Okay, this is not important. You scale and you get an energy value. but you need to know
Okay.
the proper scaling. It depends on the application. Okay,
Okay.
you can think about that the X is forget what is written there. The X is an energy loss between 0 and the primary. In our case, if you think about the silicon, actually, you would get the same distribution, a very similar distribution. The X would go from 0 to 45 MeV, since here we had a 45 MeV primary energy. And this mean value of 1.5 would be somewhere here, okay, or it's not so important. I just showed here some plot that indeed, if you are using fluctuation, it gives you the distribution of the energy. And you have these two choice for ionization using Urban model for energy loss fluctuation, or the pi model, which stands for photoabsorption ionization, which is a bit more sophisticated than the Urban, but requires much more computing time. Okay.
Okay, thank you.
Okay, so let's move quickly to the continuous step limit, because it's also a consequence that we are using we are using secondary production threshold, and we describe some subthreshold secondary photon and electron production with a continuous energy loss process. So in other words, why for example, an electron moves from the pre to the post step point, actually it will continuously lose energy. What we need to make sure actually to get again, to stay again within the limit of approximation, that in one step the particle does not lose too much energy, because if there is a huge difference, then we are out of some approximation limit. So in order to achieve this, we have a so-called continuous step limit. So not only the cross-section will limit the step in case of electrons that has continuous interaction as well beyond the discrete one. The discrete is described by the cross-section. The continuous is described by the stopping power. But also this continuous interaction, the energy loss, just to make sure that the electron do not lose too much energy within one step, especially as long as the electron has high energy. So in order to do this, Geant4 employs this function that I show here, the functional form, but on the right you can see the top. And on the y scale, what is plotted is actually the step length in units of range, which means that is the step length actually in the fraction of range. You can see the maximum step length that the continuous process can give is the range. So there will be always something there that won't let the particle go further than the range. But actually, what you see, this function works in such a way that on the y scale there is the range. So as long as the range is high, the continuous step limit will make sure that the particle doesn't go further than actually 20% of the range. But if it would be always like this, you can imagine when the electron energy would go down and down and down, the range would go down and down and down, and you keep this 20, 20, 20, then you would hardly finish the simulation. So what's happening is that when the energy goes down and the range is getting shorter and shorter, the function makes sure that we are approaching with this step limit to the range. So at the end of the step, the continuous limit will let the particle go to the range, and if there is no any other interaction and discrete interaction and nothing that would stop, and boundary that would stop the particle before this range in this last step, then the particle will reach its final position, and it will deposit all the energy eventually. So there is this smooth transition, and this function actually makes sure that the charged particles will be nicely automatically ranged out at the end of their tracking. And here I show that there are default values for this. This 20% is not fixed. You as a user, you can set with UI command what is this high energy value, whether it's 20 or 0.2, 0.1, or if you want more strict, you can go down even to 0.05, 0.02. You will apply actually shorter and shorter, stronger and stronger step limit if you lower this value, while this final range value, which is rho here, will determine the point where you start to range out your simulation. So the later you range out your simulation and the lower the d-rover range, the more steps you will do with your particle. We expect a more accurate simulation. Should not change this accuracy too much if you go with the d-rover range between 0.15 and 0.2, okay? But if you go above, then you will let the particle to make longer steps, as we are talking about only the continuous limit part. If other interactions or discrete part limits the step, it's another story. You will make a faster simulation, but probably less accurate. Okay, as a user, you can set it, and if you see, I show on the top the default value. It's also reported when you run the simulation, and you can see in the report that, for example, the particle here, electron, the process is ionization, called e-iony, and many things is reported, and one of those, among those, you can see the final range, which is 1 millimeter, and the d-rover range is 0.2. Indeed, these are the default value, and if you invoke the UI command, then after rerun the simulation, then you can see that you can indeed change this behavior, and your stepping with electron will be different than before. Okay, so that was also some consequence of applying a secondary electron and gamma production threshold. We mentioned already the regions, that they are very useful concept, but in case of electromagnetic physics, sometimes you have a complex detector where there is a small part of the detector where you would like to describe, for example, ionization in a much more sophisticated way, because you are interested so much in the details, and you would like to get a very accurate description of the interaction at that part of the detector. But you are fine with the bit less accurate but more performant description in the other part of the detector. With regions, with electromagnetic physics, Geant4 provides you the possibility to change the physics description of a given interaction in different regions. So when you apply a physics list, when you choose a physics list, you have a description that will be applied in your full detector. But what you can do, in case of electromagnetic processes, you can set for a process a model that will be used in a given region instead of another model. Okay, I show an example. Yes, here you can see a bit more details about how you use even DNA physics to simulate some particle transport in a given region of the detector, which is DNA physics, is not condensed history, it's pure discrete description. This is why you see many steps, very detailed simulation on this region B slab, while in region A and in the region A and 2 side, you will see less steps because we are making longer steps, we are using condensed history simulation. So it's really possible and very easy to do this even with UI command with Geant4. However, if you want to make it more sophisticated, you can do it by yourself. Here I show a piece of code that actually will change again back to this test EM3 example where we have just introduced previously a region where we put the liquid argon in that region. And if we would like to use electron ionization model that is a bit more sophisticated than the default, for example, you would like to use this pi model, the photoabsorption ionization model, to describe ionization in that region. I show how you can do it. It's very simple, a couple of lines. And what will happen, actually, if you run your simulation, and you see again the report, on the top you see what happens by default. You can see that electron ionization has a model that's used in actually the default region for the world, which means that the whole detector. And if you do the changes that I just showed in the previous slide and you rerun the simulation, you will see that for electron, now you have actually for ionization two models. The model that you had previously, and it's used actually everywhere in your detector, except our region, where actually this pi model is used to describe the ionization of the electron. So you can verify from just reading the printout that everything works as you expected. Okay. So yeah, here I show in more details this combination of standard electromagnetic physics that I'm talking about today, actually this condensed history approach, with the DNA part of the Geant4. That's a pure discrete simulation. There is no production threshold. They are simulating each individual secondary electron and photon by themselves. And what you see here, the red dots means actually an interaction point. So you see that indeed on the two sides, left and right, there are less interaction points. We are making longer steps because we are using condensed history simulation, while in the middle, where, I don't know, that is where the human body is, in a lab. And there is a much more detailed simulation of the interaction. So you can combine nicely the two worlds. And the last topic that I would like to mention quickly, very quickly, because actually it would require a couple of hours to discuss in more details, is the description of multiple Coulomb scattering, which is beyond already this secondary electron production threshold. However, the concept of introducing some threshold, it's quite similar. If we are using actually multiple Coulomb scattering, our threshold is the highest, but there is some other description called mixed simulation that has even a closer relation with what we have been talking so far. But we are talking about multiple Coulomb scattering today, not the mixed description, unfortunately. But let's see the multiple Coulomb scattering. Why we need to use multiple Coulomb scattering? Okay, we don't need to use. You saw that, for example, the DNA that I have been showing, the DNA physics doesn't use multiple Coulomb scattering. They will model each individual Coulomb scattering of an electron. But what they will do, let's see on the right, I show the plot. On the Y scale, you can see the elastic mean free path as a function of the electron energy in different materials. The materials are not so important. The trend of the elastic mean free path is the important. The elastic mean free path will tell you the average distance that the electron will travel between two Coulomb scattering. And as you can see, after a certain energy, it becomes constant, which means that if you have a very high energy electron, it will always go the same mean distance between two Coulomb scattering. So if you need to simulate a high energy electron, there will be a very, very high number of Coulomb scattering that the electron will go through till another interaction like a Bremsstrahlung photon emission or ionization would happen. But there are such a high number of this Coulomb scattering, if the electron energy is high means that I would say like a couple of 100 kilo electron volt, that actually simulating each individual Coulomb scattering, it's again becomes not feasible. It would really require lots of time. So what's happening in the simulation codes even for intermediate energies, but especially for high energy simulation codes, is that they employ multiple Coulomb scattering model. And this multiple Coulomb scattering model, when they are used, actually what's happening is that we practically remove from the list of interactions the Coulomb scattering. So this mean free path won't play any role when we decide how far the electron will go. So we let the electron to go a really long step, much longer than the distance between two elastic interaction, between two Coulomb scattering. And at the post-step point, we are using a model, that's the multiple Coulomb scattering model, that will tell us what is the net effect of all those many elastic scattering, all those many Coulomb scattering that actually would happen along this step. And the net effect is some angular deflection and some change in the position. Okay. So that is why we use multiple Coulomb scattering and what multiple Coulomb scattering gives us. Actually, depending on if the particle has Coulomb scattering or the Coulomb scattering is described by single or multiple scattering model, there are a couple of three different scenarios. The A is when we move from a particle from a pre to the post-step point, is that A is that when there is no Coulomb scattering, you can imagine a photon will simply move from the pre-step point R0 to R1 along a straight line. Okay, nothing will happen. Now, if the particle has Coulomb scattering, but the Coulomb scattering is described as a pure discrete interaction, so actually each Coulomb scattering is modeled individually, like in case of DNA, then the Coulomb scattering actually will participate with the cross-section, with its cross-section, in the determination of the step length. So everything is fine. Even in this case, the particle will be moved from the pre to the post-step point along a straight line. If there is no any magnetic field, I say that there is no field here, okay, just for the simplicity. When I say that it will be moved from a straight line, it's always moved from some kind of straight lines from between 2 points. But the interesting thing is here in these two cases, that actually the geometrical length of the step that the particle does, which sometimes also called the transport length, in Geant4 is geometrical, this is SG, is exactly the same like the true step length. Okay, the two things are exactly the same. It's not the case when we describe the Coulomb scattering with multiple scattering model, because what will happen actually, here in this case, the post-step point, the R1, actually is much further than in the previous case. Okay, the figure doesn't show very well, but actually this R1 is like, can be 1,000 times longer than or further than the previous R1. Okay, when we are using single scattering to describe the Coulomb scattering. So it's much longer, the post-step, the virtual post-step point that the particle goes when we use multiple Coulomb scattering before the multiple Coulomb scattering would tell its answer. Because what's happening actually is that, as I mentioned, we let the particle move much further, yes. But then after, we need to take into account that there were many Coulomb scattering happening during this step that we did not model so far. So eventually the particle would move, for example, along this blue trajectory, if we would include all the Coulomb scattering. So what multiple Coulomb scattering tells is actually tells us the final position in this case. So after each step that we do, when multiple Coulomb scattering is applied, multiple Coulomb scattering will tell us the final position. In more detail, will tell us how far we go along the original direction, and the particle will be propagated along its original direction till that point. And then it will tell us a vector that along the perpendicular plane where we need to displace the particle to get to the final position. So it tells us the final position, and it also tells us what is the final direction, the net effect of this angular deflection at the final position point. Okay. So everything is fine as long as we can eventually put the particle into this final position. Okay, because what's happening is that multiple scattering will tell all these things. The step limit will be done actually at the press step point, where we still don't know if we can go as far as we want. No, that's a more detail actually. There are more details in the Coulomb scattering that I don't really want to talk about today. Is that sometimes we can reach the final position where we should be. Sometimes, however, we cannot reach the final position because it would result in a boundary crossing that we were unable to recognize at the press step point, that actually the final position, if we go so far, that will be on the other side of the boundary. So we will do, whenever we use multiple Coulomb scattering, unless we use a very strict geometrical limit each time of the step, we will do some mistakes, and each mistake is actually happening when we cannot reach the required final position. Okay, it might be a bit cryptic, sorry for this, but that would require much more explanation in this topic. The important message is that multiple scattering will play an important role in the step limit, that how far your particle can go in a given step. Actually, electrons, if we're talking about electrons that usually have many, but in case of charged particles in general. Then, usually in case of multiple scattering in Geant4, you have different level of multiple scattering step limits. I list here the different use safety, use distance to boundary, use safety plus. If you go from the top to the down, the first one is less strict, it's a kind of default step limit. You will use a couple of mistakes, some number of mistakes. How many? It depends how granular is your detector geometry. Of course, if you are in a big volume, then you won't do any mistakes because all the boundaries are usually very far. If you have a more granular detector, then you will do many mistakes with this step limit. Okay, then we recommend to choose a bit more strict step limit that use distance to boundary, or if you need a really precise, practically error-free stepping, that makes sure that you are always able to get to the final position. It's the use safety plus step limit, especially if you are using the EM standard option for physics. Now, at the same time, the first one will give you a fast simulation. Use distance to boundary will be a more strict step limit, so your particle will stop more frequently, while the last will be even more frequently. So the time of the simulation can be even a few times higher if you are moving to use safety from use safety to use safety plus. So this is the usual trade-off between the simulation time and the accuracy that we need to face in the middle or high energy simulation. So that's more or less what I wanted to show today within this short 1 hour. The last slide contains some information about some pointers where you can find, where you can reach us, find more information, report bugs, and so on, or go to the forum to see some discussions, or if you have any questions. That's it from my side.
Thank you, Mihaly.
Yes.
Gabriele asked me to bring the questions to you now. I don't know if you want to take a drink of water briefly while I find the first question. There's been a few questions. I need to scroll up a fair amount. So I think the first question you've already answered, by Henri, is asking, is there a command to print what energy is associated to a given length cut for particle?
Yes. Normally, if you see our examples, electromagnetic examples, each of them will dump actually. You have a method for the material cut couple table that you can dump them. And if you do that, you will see actually exactly this information that I show here. Okay, this is tells you what kind of materials, what kind of material cut couples you have. What is the length, production threshold in length, and the translated energy. So from here, for example, you can see that you expect any change if you decrease your production threshold in length. If you are already, like in case of this galactic, evidently, you are with the 0.7 millimeter, the production cut, corresponding production cut energy is already the default, the minimum, below the minimum value. If you decrease further to 0.1, you won't see any difference in your simulation.
Okay, thank you. I will also go with another softball, but Patricia asked whether it's possible to set different production thresholds to different logical volumes. Certainly it was in your slides how to set different production thresholds to different regions, and the same goes for logical volumes. So I think that's
exactly. Exactly. You need to set different regions to different logical volumes, and you set to different production threshold to those different regions. Exactly like I did actually in the example for liquid argon in the test TNT.
Sarvesh says, a very common technique to measure bunch width of ion beams is to hit a target by a pulsed ion beam which produces gamma rays. And then by measuring full width at half maximum of the gamma ray signal in time, we determine the bunch width of ion beams. Can we simulate it in Geant4? I think the answer is very simply, we have time in Geant4, and of course.
Yes, I think.
So, sorry, Alex also, I think, responded. His comment was, you can certainly simulate an instrument response function like this. It's done all the time for diagnostics, to send all the starting particles at a certain time and extract the signal with a time histogram in your simulated detector. I do it for Cherenkov detectors, gammas in, optical photon signals out. Thank you, Alex. Where can I find the UI commands for muon multiple scattering, asks Laura.
UI commands, thanks to Vladimir, is an evolving, forever evolving set of commands. What I would tell is that there is I think I will post the class where you can find all the UI commands that I'm talking about, where we define them. That's the best place. Wherever because it depends also on your version, whether a command is available or it was introduced in a later version. What I usually do, I take the version, Geant4 version that I'm working with. I go to this class that I cannot recall the exact name. I don't want to say anything. I will post it, okay, on this forum.
There are several ways how to do this. Of course, first of all, you are right to go to code and see all commands. Then to start interactive session and simply make a list, ls within subdirectory electromagnetic, and you see all commands which are available. It is two ways where you can reach them. And finally, go to application developer manual, physics and tracking. There are a list of all commands. Hopes that they are corresponding to reality for each release of Geant.
I think that one thing to mention is that typically commands could be added, but they are less frequently deleted. That commands would be deleted typically only if they're confusing, or if there's a significant change and they're made obsolete in the mid-time, and typically deleted in a major release, or if it's really important, maybe a bit earlier. I don't know, is that a fair assessment?
In an interactive session, if you have application with interactive session, to study all list of commands is the most fast, I would say. But for experienced person, as Mihaly said, go into the class and read comments. Of course, it is.
Usually these classes are in the category, because the comments are organized. If you see the different components, you see the category, and the class, if you go to the class, to your source code, they will end with the name of messengers. What is this for the EM, Vladimir, the G4 EM parameter messenger?
Yes.
Yes.
But there are also two extra messenger, low energy parameter messenger, and extra parameter messenger. There are three messenger classes, and it is possible to identify.
If you go there, you really see because lots of text are there. So you go open, look for the muon, and then you find all the muon related.
Okay, thank you. So Sarvesh is asking as an application-related question. Again, can you design a foil stripper for MEV heavy ions, which would lead to multiple ionization, which can lead to multiple ionization of heavy ions and finally result in higher charge states? Is this physics model available in Geant4?
I would let Vladimir to answer this.
John, sorry, I was interrupted. Please repeat the question.
Sure. He is thinking about designing a foil stripper for MEV energy heavy ions. This can, of course, lead to multiple ionization of the heavy ions and thus reach higher charge states. Is our physics models available in Geant4 to simulate this?
We have, if you use option for EM physics, you use a model which is utilizing ECRO 73 data for stopping powers in MEV region for heavy ions. So general ionization will be reasonable, but model which simulate exact charge state is available only for DNA physics. In typical application, which we use for HEP or for medical applications, we usually are a condensed history approach where we compute DDX and delta electron production, but not each inelastic collision.
Okay, I will try and summarize that in my response, but I think it's complicated enough that it would be good if you actually add that in the text. In Mathemos, please, Vladimir. So I think that was the last question that I have, unless someone, if I've missed something, can someone please jump in? And after that, we have the chance to give, to ask questions of Makoto, who's kindly logged in and can answer questions about yesterday's lectures. If someone who missed yesterday's lectures but is present would like to ask questions of him. So please jump in, either people whose questions I missed, or you simply want to ask an extra question of Mihaly, or if you have a question of Makoto, which you didn't have a chance to put yesterday, potentially you had not joined yesterday. Okay, if there don't seem to be any questions, either one or the other, according to the timetable, there was a 15-minute break here. We've overrun it, but if everyone's okay, I suggest that we take an 8-minute break until 10:30 for people to catch their break and get a quick cup of coffee